Hi, I'm Antonio Sala, and in this video we will conclude our basic outline on what Bayesian optimization is. In previous videos we discussed the basic methodological ideas. We'll review them in a couple of minutes, and in this video we will put forward the application use cases in which Bayesian optimization is mostly employed, and a couple of remarks on the relationship between deterministic optimization and those statistical optimization methods. The basic idea in deterministic optimization was, having this kind of expressions that I can evaluate in milliseconds, and I can differentiate them, obtain gradients, Hessians, and approximate them by tangent planes, tangent parabolas, etc. And the basic idea in Bayesian optimization was thinking that the value of the function was a random variable with a certain mean and variance, and that the value of the function was unknown until I evaluated it. But, prediction formulae are based on statistics. We have a mean function, some 2 sigma confidence intervals, for instance, 95%. But for the function to be continuous, the random variable at this abscissa and the random variable at this abscissa, the covariance between the values of the function at 2 close points needed to be defined with a so-called covariance kernel, so that the statistical correlation between f of a and f of b tended to 1 as the distance between a and b tended to 0. So the theory of all that is the framework of Gaussian processes, and its properties, continuity, differentiability, whatever, need of course a rigorous development that is out of the scope here. But with this mean, variance and covariance stuff, we described our prior knowledge on the function we are going to optimize, and we can encode some smoothness, bandwidth, and other characteristics with this Gaussian process stuff. We also discussed the fact that most Bayesian optimization techniques iterate these steps in here. We have this prior, we have some historical record of samples, so we obtain the posterior with some formulae from the posterior, normal, conditional stuff, and then we carry out a statistical analysis of the posterior to determine which would be the best choice for our next sample. So Bayesian optimization is a kind of experiment design, let's say, and once I get the next sample, I evaluate it, maybe with some measurement noise, and I repeat and repeat and repeat until I am fairly sure that I got the actual global optimum. The details on the posterior computation are based on these formulas. Don't worry if you don't understand them at this moment. This is just a glimpse on what things are about. And the statistical analysis can also be carried out by many different options in literature, and explaining each of them would be the material for a separate video, but again, this is just a fast outline on what these things mean. You just need to understand that these statistical analysis tools will somehow compute what intuitively I see here, that this blue region is the most likely region in which the global minimum will be. So maybe the best choice, is trying to see which is the value the function takes here, and if it is this thing, then I update the posterior and I repeat and repeat. So that's the basic methodology. So these were the ideas we reviewed in previous videos. Now let us discuss application use cases. So when is Bayesian optimization recommended? Well, the first setting in which we can apply this is what is called experimental optimization. What does it mean? Well, it means that I don't exactly know the analytical expression of f, so I cannot code it in MATLAB, let's say, or Python or whatever. For instance, the first usage in practice of this Bayesian optimization stuff was in mining. Under the name of Krieging, this Gaussian stuff appears, and that was the surname of a mining engineer, Daniel Krieg, which worked in South Africa in, finding the highest concentration of some mining ores, and then his master's thesis and the like was the first use case of this Gaussian process stuff. So it started up in geology and mining, at least in the application point of view, stochastic processes and the like were studied in abstract terms by Einstein and colleagues. But okay, we engineers started thinking in this in mining, because we don't have a formula for the concentration of iron as a function of the position in some valley of my drilling rig. So we have a basic model from whatever geological computations or prior expectations, let's say, and then we drill at several places, obtain iron concentrations, and we interpolate with this kind of interpolation stuff. And then in mining, this is called kriging. Then this experimental optimization is the basic usage case. In fact, these statistical methods can of course incorporate measurement noise, in the sense that if I drill at some location, maybe I am unlucky and there is a lot of iron, but I extract just a sample of a sandy rock with no iron in it. But if I move 20 centimeters left my drilling sample, then I would have obtained a lot of iron. So when experiments are not repeatable, when they have a lot of noise, we can incorporate that uncertainty as a statistical model. So this experimental optimization of noisy samples of an underlying mineral concentration of which I don't know the formula is the basic application arena for Bayesian optimization. But there is a second context in which Bayesian optimization is used. And in fact, maybe it's the most popular in computer science, which is using it when the deterministic evaluation of my function or my optimization, let's say, takes a lot to compute. For instance, I may be training a neural network to classify pictures of cats. Then training that neural network takes, let's say, 300 hours of computing in a data center, consuming a lot of energy. And what I want to optimize in that context is the number of neurons, the learning rate, or other what we call hyperparameters of the learning task. Why the learning rate is 0.1 instead of 0.6, why the number of neurons is 85 instead of 200, why the number of layers is 5 instead of 6. So if I just blindly try different values of those hyperparameters, then I take 2 weeks of data center usage to get my new model. So well, maybe in some cases a crude approximation plus some statistical uncertainty error there, which we invent because the result is deterministic. The optimal setting of the neural networks is whatever, but okay, we invent some statistical error bands. And in some cases then we spend a couple of minutes with this statistical Bayesian optimization stuff, deciding which will be the next value for the learning rate, instead of just guessing at random and spending 2 weeks training my new neural network. So this is a second usage case in, neural network training or, computational fluid dynamics optimization, which also take a lot of time or whatever. Then we may decide configuration of the different runs of the learning or fluid simulation with this Bayesian optimization stuff. It is not formally needed. The output of my fluid simulation is deterministic, but deciding its configuration between runs to avoid wasting 300 hours of computing time is in some cases done with these Bayesian optimization ideas. So this is the second usage case. We have experimental optimization, we have deterministic optimization, but taking hours or days to finish. And then when this Bayesian stuff is not recommended at all, well, I will never use Bayesian optimization to optimize this kind of silly toy problems in which I can compute gradient, Hessian, whatever. Even I can brute force evaluate the function in a fine grid. So, I would never do Bayesian optimization in this. I would call whatever deterministic optimization routines I have at hand. But, well, maybe you see some videos optimizing these kind of simple functions with Bayesian optimization, but those are tutorial videos in order for the viewer to understand the behavior of Bayesian optimization. Because, if you know the underlying true function, then you can see how the samples approach the optimum. So in tutorial videos, you would do Bayesian optimization with this stuff, but not in realistic applications, of course. And then regarding the realistic applications, well, the idea is that these posterior statistical models with this formula and these 8 different ways of doing the statistical analysis of the posterior are somehow fast and efficient and accurate if the number of decision variables, well, in this case, is just one-dimensional. So if you have 1, 2, 3, 4, 5 decision variables, let's say, then, okay, this is reliable and reasonably fast. But if you are going to do Bayesian optimization with 10, 15, 20 variables, then okay, it's no longer clear that it helps. The statistical analysis may take a lot. The posterior computation may need to invert large covariance matrices, and well, Bayesian optimization is not advised when you're optimizing more than 15, 20 variables. But okay, if you are in an experimental optimization problem in which you have 20 variables to optimize and you don't have analytical models of the function you wish to optimize, then wow, that's a hard problem. Optimizing 20 things in a very uncertain underlying function, it's a very hard practical problem. So you'd better try to get some theoretical approximation of that. Otherwise, finding the optimal of something in a 20-dimensional decision space with no theoretical model apart from this kind of interpolation formula is kind of hard. This is another case in which I would maybe not use Bayesian optimization, but maybe I would not be able to use anything. So good luck. Then, okay, we have, the experimental optimization clear framework for which Bayesian optimization was devised. This fluid dynamics, neural network training, whatever stuff in which, well, it was not initially thought for that, but it is widely used also to avoid taking hundreds of hours to compute. And then we have the sign of X minimization, in which I would never use Bayesian optimization unless I am making a tutorial video on it. And I would never use it optimizing 25 variables, of course. Then we'll finish the video with a couple of remarks on the relationship between deterministic and Bayesian statistical optimization. In particular, the first remark is that determinism is a particular limit case of statistics, in the sense that if I reduce my variance so that I have my mean function plus minus 10 to the minus 8 uncertainty confidence bounds, okay, then that's deterministic. So for a mathematician, determinism must be a particular case of statistics, and deterministic optimization, let's say, should be that limit case or should have a statistical interpretation. For instance, just least squares fit of a linear model can be given a statistical interpretation if I think that my samples are corrupted by normally distributed noise, whose probability is a function of the squared error exponential, and then the log probability depends on the squared error, so least squares minimization can be embedded into a statistical interpretation. Okay, I am not delving into the details. I mean, this deserves further thinking, but okay, I'm just outlining the basic idea. So, if you are a statistician, everything is statistics, even deterministic optimization. But okay, that's kind of a conceptual remark, and what it is called Bayesian optimization in applications is usually this kind of Gaussian process manipulations and statistical analysis on where the optimum is and whatever. Even if from a unified, the great scheme of things, deterministic and statistics are two perspectives on the same problem. But okay, we have some intermediate stuff, such as semi-parametric Bayesian optimization, in which we add this kind of parametric models plus Gaussian uncertainty, whatever, to our optimization. So we know that everything is part of the same great scheme of things. Of course, we can think on this in a more general way. But again, in this introductory video, I just want you to just get a glimpse on the possibility of this and not really understanding in depth the meaning of all these ideas. Then, the last remark I'm willing to explain in this video is the fact that, okay, in some cases, if I want to minimize this thing, x squared cosinus of 3x, it will have this kind of shape, parabolic plus cosine. So it will have a lot of local minima. And then if I start a gradient descent method in here, it will end up here. But if I start it here, it will end up here. So, derivative-based optimization just goes down to a local valley, local minimum, but maybe it's not the global one. So there are deterministic optimization problems in which we throw the dice, for instance, in the initial conditions. This is what we call, multi-start options in deterministic optimization. And in fact, the general class of models in which this kind of random stuff is done is kind of named directed random search algorithms in deterministic optimization. But okay, the underlying function we are modeling is not having a statistical model. Okay, it's deterministic. We are dealing with deterministic optimization, even if we throw the dice in this directed random search, genetic algorithm, evolutionary swarm, whatever interpretations of optimization. But this is not Bayesian optimization. This is just a way to escape the locality of derivative-based deterministic optimization. Okay, so with these two remarks and our application discussion on Bayesian optimization, we will conclude our video by just summing up what we have seen in these introductory videos. If we have a function that is fast to compute, then we will use deterministic optimization. And if we have a function whose evaluations are given with some measurement noise, or even I do not have a closed form for it, then I will use statistical methods for optimization. And in fact, I may even use statistical optimization even for deterministic problems in which evaluating my function takes hours to execute. So maybe I play a bit modeling the uncertainty on some rough approximations to decide some configurations for neural networks or fluid dynamics simulations to avoid wasting hours of computing time. The other idea of this series of videos is that Gaussian stochastic processes are the tool of choice in most of the developments of Bayesian optimization in engineering and computer science. And we also gave some last remarks in that there is a unified grand scheme of things in which everything is statistics, if you are an statistician, and there are also techniques of deterministic optimization in which we throw the dice to avoid getting stuck in local minima, but they are not part of the Bayesian optimization toolbox, at least in principle. So, with these final conclusions, we end the video. Thanks for watching.